a tree or a binary tree, in this case a binary search tree, as an array is fine if the tree is complete. So basically it's not biased towards the left or anything, it's complete. Or otherwise the array representation is not appropriate. In which case we just use a linked structure implementation like we have seen in linked lists. So each element of the dictionary, for example, element 1 has got key 1, and value 1, and we are going to add a pointer. So if you remember, in linked lists, maybe it's better to explain it this way. In linked lists, our elements we had our elements as key and value, and then we added a pointer. So key 1, value 1, and then key 2, value 2, etc. So this was our original element, and we added a pointer in order to build the linked list. And we are going to do the same here, but instead of one pointer, we are going to add two pointers, one for left and one for right. So this is how it looks like. Key 1, value 1, and there is a pointer to the left and a pointer to the right. The pointer to the left points to the left child. So every record in our dictionary, we augment it with two pointers. One for the left, key 2, value 2, pointer to the left, pointer to the right, key 3, value 3, pointer to the left, pointer to the right, and you continue doing that until you have null pointers, etc. Okay, so it's very similar to the linked list, but in the linked list it's linear. This is why we called it linear data structure. It just goes one. It has one kind of child. Okay, it just goes linearly. However, with a tree we have two pointers. One goes to the left and one goes to the right. Okay, so that's how it works. Obviously, in main memory, you will have two addresses after. Instead of one address storing one pointer, you will have two addresses, consecutive addresses, because we said a record is a consecutive. It's just like an array. It's contiguous as well. So in main memory, this is how one node of the tree is going to look like. Key 1, value 1, address 1, which is the address of the left child, and address 2, which is, okay, I'm not drawing it right way, but you get the idea. It's because they are all together, because the record itself is a contiguous data structure. So in this lecture, we are going to assume that the tree is represented as a linked structure, because for our purposes, this is more efficient. Why it's more efficient? It wastes pointers, obviously. However, the amount of space that we waste in pointers is smaller compared to the space we waste in this space fillers when we use the array implementation, especially that we cannot guarantee that a binary search tree is going to be a complete tree, nicely balanced from the left and from the right. As we said, a binary search tree can very much end up looking like a linked list, in which case we waste a lot of space for very few dictionary elements. So we are going to assume this representation for the rest of the lecture. Finally now, we can talk about the three operations that we need to be efficient. Okay? So we have three operations that we need to be efficient in our dictionary, and they are lookup, insert, and delete. So how are we going to do lookup and insert and delete? So this slide is basically just telling you, explaining the data type that I'm using in the pseudocode. So the tree is made of nodes. Each node has got the type element. Node.key stores the key of the element. Node.value stores the value, whatever it is. The value can itself be a record. We can have .value 1, .value 2, .value 3. Well, you get it. Value is just anything in the record which is not the key we are using to retrieve, insert, or delete the element. And finally, node.leftChild is points to the left child of the node, and node.rightChild points to the right child of the node. So now let's talk about how we do lookup in a binary search tree. Right. So this is our binary search tree. So that's some binary search tree, and we want to search for the element 6. So it's quite intuitive how we do it. So can somebody just explain to us how we search for the element, or any element x? Let's say x that we want to search for is 6. How do we search for that? Yeah, you got the idea. So we always start our tree operations at the root. Okay. So when we look up, when we insert, when our tree operations at the root. Okay. So when we look up, when we insert, when we delete, this is our starting point. It's like the header in the linked list. So the root is always our starting point. So we are searching for the key 6. Okay. So what we do, we compare it with the root. Is it equal to the root? If it's equal to the root, if this was 6, then we are done. If it's not 6, then we should go either left or right. We should either search for it here or search for it here. How do we choose? We compare. We compare this value with the root. So 6 is smaller than 10. And we know this is a binary search tree. If 6 is smaller than 10, then if it is in the tree, then it should be here. So we go to this part and start searching again. Is this 6? No, it's not 6. Now, is 6 bigger than 5? Or is it smaller? It's bigger than 5. So 6 must be here if it is in the tree. And then we go to 7. Is 7 equal to 6? Nope, it's not. How is 6 compared to 7? It's smaller. So it must be in this small subtree here, if it is in the tree. And then we finally find that, well, we got 6 here, so we are done, and we return 6. Now, if we are searching for 13, for example, again, we start at 10. 10 is not equal to 13, and 13 is bigger than 10, so if 13 is in the tree, it must be here. And then so we go to 12. It's not equal to 13, and 13 is bigger than 12. So if 13 is in the tree, it must be here. And then we go to 15, and 15 is not equal to 13, but we know it's bigger than 13. So if 13 is in the tree, it's going to be here. And then we go to 14. 14 is not equal to 13, and it's bigger than 13. So if 13 is in the tree, it must be here. But this is an empty tree. There's a null pointer here. So we find null, and hence we say we did not find the node that we are looking for, the key 6. So this is binary binary search, which is the same binary search that we know that we use when the array is sorted. We compare to the middle element, and then we branch left or right depending on the comparison outcome. So in terms of pseudocode, it's just like what we said. We compare to the node. If it's equal to the node, we return it. If it's not equal to the node, then we recursively compare to the left child or the right child. So the first case, the base case, if there are two base cases. So if the node is null, like when we searched for 13, 13 was not in the tree. And we knew it was not in the tree because we reached a null pointer. So if we reach a null pointer, that means the node is not there. So we either raise an error or just say it's not there. Otherwise, so basically in this code, we are searching for this element, for key to search. This is X, key to search is X. And the current node is basically what we are doing. So the first thing we're going to do is to call lookup on the root. So the first thing is to call lookup on the root. So what it does, root is not null, okay? Let's assume the tree that we have used before, and we are searching for element 6, okay? So the root element was not null, so it's not null, and it was not equal to 6. So what we did, we compared the key we are searching to the key of the current node. If it was larger, then if the current node was larger than the key we are searching, then what we did, we repeated the operation in the left subtree. If it was smaller, we repeated it in the right subtree. So the next time, so this lookup is just a recursive call, right? So that's lookup, and we are repeating it right here, and we're repeating it right here. So this is what we did in our this tree. It's dark, right? So we called lookup here, and when it was not equal, we compared to the key, and we called lookup here. If it was not equal, we called lookup here. It was not equal, we compared and called lookup here. So it's the same operation we apply in every node depending on the comparison outcome. So it's a recursive function, and hence the recursion that you see in this code. It's pretty much self-explanatory. So this is how we do a lookup. Now, about the complexity of the lookup, it depends on actually the tree that we have. Let's say this was our tree. Okay. Let's say we have n elements in this tree. So this is a nice balanced tree. Okay. If this tree has got n elements, then what is the complexity of the lookup in the worst case? Big O of? Yeah, log n, because we are the number of, or the amount of steps that we do every time is half, because we're here. When we go to this stage here, when we choose this subtree, we have already discarded half of the subtree, and then when we choose that, we already discard that. So every time we are throwing away half of the elements. So we throw n over 2, and then we throw n over 4, and then we throw etc., etc. And we said that this is going to be log n. Okay, you can put in numbers and convince yourself. that the number of the worst is so the number of nodes here n is actually what? 8 plus that the number of the worst is so the number of nodes here n is actually what? 8 plus 4 12 plus 3 15. And in the worst case, if the node is here, all we have to do is to go 3 times. So we need 3 steps in order to find the node, or 4 steps in order to say, no, actually we need to call lookup, and then lookup, and then lookup, and finally lookup here. So it's 4 in order to find the node. So n is 15, which is almost 16, 2 to the 4, and 4 steps is actually the log 2 of n, the log 2 of 16. So the number in this nice balanced tree, the number of recursive lookup that we need to make is actually log n. Okay. However, the tree can be horrible. The tree can look like that, in which case the complexity is going to be n. Okay, if the dictionary has n elements, the complexity is going to be n. Okay, so the complexity is going to be between log n and n. Okay, and actually we call it h, and h actually is the depth of the tree, because when we said it was log n here, log n actually is the depth of the tree. We said the depth of the tree is, this is depth 0, this is depth 1, this is depth 2, this is depth 3. The depth of the node, no, we did not explain that. We said the depth of a node, this depth of the node is 0, the depth of this node is 1, the depth of this node is 2, etc. Now, the depth of a node is the number of edges that separate the node from the root. So there is no edge that separates the root from itself, so the depth is 0. The depth of this node is 1, because there is one edge which separates it from the root. The depth of this node is 2, because there are 2 edges that separate it from the root. Now, the depth of the tree is the depth of the deepest node. Okay? So we have defined the depth of a node. Now, the depth of a tree is the depth of the deepest node in the tree. Now, the deepest node here is any one of these, and the depth h equals log n. When the tree looks like that, the deepest node is this, and the depth of the tree equals the depth of the deepest node. And because we have n of these, so we have n edges, so it's going to be big O, h is going to be big O of n. So the depth is going to be between log n and n. So we say that the complexity, asymptotic complexity of lookup is big O of h, where h is between log n and n. Now, just a question for you. What is going to control the value of the depth? Before that, we use the term h because it's the most common one, because sometimes we use the height of the tree as opposed to the depth of the tree. I mean, both are symmetric. The highest tree, the deepest tree. So you can either look at it as depth or as height. This is why you see the h here. It's from height. You can either look at it as depth or as height. This is why you see the h here. It's from height. So height, depth, it should not confuse you. So my question, what is going to control h? I have a dictionary. Let's say a dictionary has got elements with keys 1, 2, 3, 4, 5. Okay? So 1, 2, 3, 4, 5. And I want to build a binary search tree. Now, can you show me a tree which is balanced? 3. Where is 2 from here? Okay. 4. Okay, so the depth here is 2, and the tree which is completely unbalanced is, for example, 5, 4, 3, 2, 1, where the depth is 1, 2, 3, 4. Okay, so this is balanced, this is unbalanced. But what is going to control this is not exactly balanced, but this is what we mean. This is like more evenly distributed than this one. My question is, what is going to control the depth 2 and 4? Why do we get 2 here and get 4 here, although we are using the same number of elements? Okay, so the same elements which are here, but why is this tree like that and why is this tree like that? It depends on what? On? Yeah, but the programs do not write themselves. It depends on the order of insertion. Okay? If I say this is what we will see next in the slides. So we have a dictionary of elements 1, 2, 3, 4, 5, elements with keys 1, 2, 3, 4, 5, and I say I am first going to insert 1. The next thing I'm going to insert 2. Well, I am forced to put 2 here. The next thing I'm going to insert is 3. Well, I am forced to put 3 here. There's no other way. And then 4. I am forced to put 4 here. And 5. I cannot put 5 anywhere else. I must put it here. But if I say the first element I'm going to choose is 3. I put 3 here. The next element I'm going to choose is 5. I put 5 here. The next element I'm going to choose is 4. I put 4 here. There is no other place. And then 1. Okay, 1. And then 2. Okay, 2. So as you can see, the order of inserting elements is going to control the depth of the tree. So here we put the keys in order. We got a linked list. And here we did not put them in order. We put them in another order, and we got this. We got a linked list. And here we did not put them in order. We put them in another order, and we got this kind of hexagon or whatever. Not a hexagon, pentagon. Okay. So the next thing we're going to look at is actually insertion, and we have already kind of covered it in this example here. So there's no big deal about insertion. So again, insertion, we start with the node, and then we look at the next node. If it is smaller than the current node, it goes to the left. If it is larger than the current node, it goes to the right. Right? So that's how we build a binary search tree, by making these insertions. So insertion is very similar to lookup. So we are going to go down the binary search tree, and so we go down the binary search tree and compare elements until we find a null pointer where we can do our insertion. So it's a recursive function, and it's very much similar to the binary search tree, to the lookup in a binary search tree. Again, what is the complexity of insertion? Huh? Yeah, it's as well. It's big of h as well, and that's because we are going first to find the place where we do insertion. Let's say the next thing I want to insert is 6. So I go here. It's not a null pointer yet, so I have to go right. It's not a null pointer yet. I have to go right. Right is a null pointer, so I create a new node here and call it 6. So there is lookup first to find the position So lookup, we know it's big O of h in the worst case, and then creating a new node, creating a pointer to the new node, that's big O of 1. That's easy. So the total of these two is big O of h, because big O of h is dominates constant. Constant is dominated by anything, right? So that's why insertion is going to be big O of h, where h we know varies from log n to n. Do you have questions so far?
No.
And that's because everything is clear, or everything is just nonsense?
Clear.
Right. Now, the next operation is going to be delete. And delete, we are going to look at 3 different cases, depending on the node that we are going to delete. I think I have something on the slides. Right. So this is a tree. It's a binary tree, and more than that, it's a binary search tree. And we have nodes x, y, z. We want to delete x. Let's say what happens when we want to delete x or y or z. We are not going to delete them one after the other. Okay? We just want to see what happens when we delete x, and then what happens when we delete y, and then what happens when we delete z. So if we want to delete x, all we have to do is just, and then what happens when we delete z. So if we want to delete x, all we have to do is just remove the node, cut the pointer, and that's it. We have removed it. Right? We don't care much, because x does not have any children. It's a node by itself. If we delete it, nothing is going to happen. So deleting x is just removing x, and that's because it has 0 children. Now, how about deleting y? Y has got 1 child, right? Now, in order to delete y, all we have to do is replace it with a child. Okay, so to delete y, all we have to do now is to replace it with that. And that's fine. Why? Because 20 is larger than this, and 15 is larger than that. So this, if we put this to the right of this, it's fine. If this was the left child, if it was 14, for example, then we can still put that, because this whole tree here is to the right of 10. So we can always put the child instead of the parent, and the property of the binary search tree is still going to be maintained. So when we delete a node with no children, we just delete it. If we want to delete a node with 1 child, what we do is we replace it with that very child. Okay? Like that. Okay, now we want to delete a node with 2 children, like z. What do we replace it with? Replace it with a parent? Okay, we cannot replace it with a parent for sure. If we put 15 instead of 20, then we will have 17 to the left of 15, which is not right. So what do we replace it with? Can we replace it with 18? And that's because 19 is going to be to the left of 18, which is wrong. Can we replace it with 19? Yeah, we can replace it with 19. Can you replace it with 22? Now, can we replace it with 25?
No.
If you put 25, you will have 22 to the right of 25, which is not right, which is not correct. So as you can see, we can replace this node with either this or this. Okay? Um, these two nodes, they have special names. This is called the in order predecessor, and the other one is called the in order successor. What is the in order predecessor and successor? In order predecessor.